Yeah, so it's my pleasure to introduce today's speaker, Karthik Elamvazhuthi, who received his BTech degree in mechatronics from Manipal Institute of Technology in 2011, and went on to receive his master's and PhD degrees in mechanical engineering at ASU in 2014 and 2019, and that's where we crossed paths because I also did my PhD there. Um, After the PhD, he went on to be a CAM assistant adjunct professor in the Department of Mathematics at the University of California in Los Angeles, then a postdoc in the Department of Mechanical Engineering in the University of California, Riverside. And from 2024 onwards, he's been a postdoctoral scholar at Los Alamos National Laboratory. And today he's going to give us a talk called Control of Nonlinear Systems using denoising and diffusion models. So please take it away.
All right. Oh, yeah. Thank you, Morgan. You guys can see my screen, right?
Yes, we can.
Okay, great. Yeah, it's thanks for the invitation, and it's nice to be presenting my work, which I did at UC Riverside. So it's about a year old. So yeah, so a lot of you must have heard of diffusion models, which is a kind of one of the big workhorses of your favorite AI tools, such as ChatGPT. Like OpenAI has DALL-E, and so the method behind the image generation and even text generation, one of the methods is based on diffusion processes. So the question that we had was, how can we apply, given the success of these methods in image generation and machine learning, can we apply these methods for control problems? So that's the topic of my presentation today. And more broadly, the method of diffusion models and generative modeling falls under the topic of manipulating probability densities. So where do probability densities come in, and why are we interested in manipulating probability densities? So these serve as models in several situations. So my own background, when I was at Arizona State University pursuing a PhD, was in controlling huge swarms of robots. And one natural way to model huge swarms, and as is done in, say, fields such as math biology, is to model them as a continuum. And then the question of how do you achieve self-organization in a swarm can be translated to how do you control this blob of mass to achieve some sort of desired behavior. Say you want to construct some kind of a structure, or you want to monitor some region. And another instance where probability densities come into play is if you want to manage uncertainty in some way. This is, for example, happens when you have a robot that's is doing some surveillance and mapping out some environment. So one way to model uncertainty is using probability densities. And of course, one of the most modern application of manipulating probability densities comes in machine learning itself. So on the one hand, my today's topic is about how do we apply what we know from machine learning to control systems. We can also go the other way. If manipulating probability densities can be framed as a control problem, similar to driving a car, can we apply techniques from automatic control to machine learning problems? So, yeah. So while there are several of these applications, let me review a simple instance of the classical control problem, which we can reframe in terms of manipulating probability densities. So one such example is is the unicycle model. Oh, I think there's some kind of echo. Okay, it's gone. So one such model is the unicycle model, which is a standard first model used for prescribing the motion of a robot. There are two control parameters. There's the turning rate, right? So you're trying to steer your car this way and that, and there's the forward and backward motion. And while this system has been studied a lot, it's known to be in some ways a notoriously hard control problem because of its certain mathematical properties. So and the standard problem is that you have some initial set in which the robot is initially positioned, and you want to get it to some target set. So, for example, this instead of a ground robot, this could also be a drone trying to, get your Amazon Prime package delivered on time. Now, there are several methods to solve this problem in control theory, but one of the distinctions in my work is to view this from a different point of view. So instead of controlling a set of initial conditions to a target set, we frame this in terms of probability densities. So what if we, instead of describing the position of a particle in terms of a set, we described it in terms of a probability? So that is, we're saying that there's a probability of finding the robot in some initial condition in some corner of your room is a certain quantity, and another corner is another quantity. And now the parameter that we are trying to control is the probability density itself. So again, this is just a reframing of the problem. And you might ask, why should we do this? And one of the reasons for this is that from a mathematical point of view, the set of probabilities has a completely different structure than the set of sets. And for example, one such a property is that the set of probabilities is convex. So when you look at the mathematical structure of the resulting control problem in terms of probability densities, this convexity can be beneficial. And another property is that, for example, if you think in terms of controlling a point from one configuration to another, classically, your system might be nonlinear in terms of the state. Whereas if you think in terms of probability densities, magically it becomes linear. And linearity is a wonderful thing to have. So this is one of the reasons why we want to do this. So I showed you an example of the class of model, example of a model that we would like to consider, the unicycle model. But the method that I'm going to present applies much more generally to a class of models called the control affine class. And this class covers a lot of important examples from applications such as robots, satellites, thermal heat plates, what have you. And in fact, if you take any general control system of the form x dot is equal to f of xu, you can do state space extension and convert it into this form, where you have these so-called control vector fields along which you can move the system. For example, in the case of the unicycle model, these were the turning direction and the forward and backward moving direction. And then you have the drift of the system, which could be another quantity. For example, this could be a certain amount of inertia in your system. So these are well studied in control theory. So now, as I said, instead of modeling the system in terms of the state of the system, as is classically done, we want to instead frame this problem in terms of the probability density of the system. So in order to do that, we need another system of equations which shows you how the probability density of the system evolves. And this is done by the so-called continuity equation, which is well studied in in theory of fluid flows, it arises. So it essentially tells you how the probability density of the system evolves under the action of the flow. So for example, in this animation on the left-hand side, you have like several initial conditions evolving according to the vector field. And on the right, you can see how the probability density evolves, which it can be shown evolves according to this continuity equation. So in terms of this equation, the problem is instead of going from an initial set to a final set, the problem is go from this initial probability density to some final probability density. So this kind of description, going from state level description to probabilistic description, has been done a lot in dynamical systems. In fact, this has especially in theory of ergodic dynamical systems, this is a standard way to understand chaotic systems, because on the one hand, at the state level, chaotic systems can be very intractable to analyze and identify. If you look at them in terms of the probabilistic description, they're much more manageable and you see a much less stochastic behavior. So so there have been a lot of recent studies on how to control probability densities. One such important field of study is this so-called optimal transport theory, which basically poses this as an optimal control problem on the set of probability densities, which is standard given the sense that given that we have a new dynamical system, which is the continuity equation. It's natural to pose an optimal control problem for the continuity equation. Of course, this has certain drawbacks that you have to solve a constrained optimization problem. And though we have gone, the continuity equation is a linear equation, it's still an infinite dimensional equation because it's a PDE, a partial differential equation. So it can be computationally hard to solve. So it's similar to how you can solve an optimal control problem by solving the Hamilton-Jacobi-Bellman equation, but you've increased the dimension of the problem. So you still have some curse of dimensionality, though the curse of nonlinearity has gone. So then there are a lot of other methods, such as mean field control, and a lot of them have like several issues. The issue that's most severe is computational in each case. And situations where the computation is not an issue, it's usually restricted. For example, you have the so-called covariance control, which is usually restricted to linear systems, and you're trying to control a system from some Gaussian family to some target Gaussian family. So you can rewrite this in terms of Ricart equations, which are have a long history in linear control theory. So given these computational challenges, what can we learn from generative modeling in AI? So the generative modeling in AI is a very similar problem, except it doesn't have the constraints coming from control. So you have a set of images, and the goal is you want to sample from a set of images. And but there's no restriction on how you get these images, right? Like you can go to the sun and come back, and there's no constraint coming from controlling a car. So how is this done in generative modeling? So in order to motivate how we will solve the control problem, it's interesting to first look at how this used to be solved in machine learning and what were the drawbacks of solving it this way. So one of the first ways to solve this was similar to how I had initially posed the control problem. You start with a set of initial conditions. In this case, there's just some images with noise. It's just pixels just randomly noised out. And based on the data, you are trying to learn a transformation that takes you from these noisy images to these meaningful images. So based on these available pictures of panda or cat or your favorite superhero, you're trying to learn this map that would ideally take you from some Gaussian distribution, which is easy to sample from. You can write a one-line Python code for it. And it would eventually spit out some whatever favorite image that you have. And this is one way to do this is by running so-called the Langevin equation. So the Langevin equation is nothing but doing gradient descent down a potential. This potential being described by this function v here, and you perturb with it with noise. And what the unknown here is this potential V, which depends on the data. And that's what we're trying to learn. So if we can learn this potential, we can map these noisy images to these meaningful images. And now you might ask, why is that the case? Why would these learning this potential do that? And the reason for that is that the behavior of the corresponding probability densities. So it turns out that if you have a potential V that you perturb your Langevin equation according to, in the limit, the probability density ends up converging to the exponential of this potential. So we are modeling the set of meaningful images using this probability distribution exponential of minus v, which is also known as the Gibbs distribution. So this is the idea behind a classical way of doing machine learning. That is, you try to identify the v, the potential v, so that your initial noisy images will eventually end up on these meaningful images. Now, what was the problem? What is the problem with this method? The problem with this method was that there are some theoretical issues when it comes to using this method to map noisy images to meaningful images. So one is the performance of this method depends on how fast you can converge to the target distribution. And this depends on the convexity properties of the potential. And so in order to attain fast convergence, you need this potential to have nice convexity properties. And so which means that if you draw out the V, it should have a nice, it shouldn't have multiple local minimas, right? And this would affect the convergence. And you can think of this in terms of, so if you had multiple minimas, it can take basically a system to go from one minima to another extremely long amount of time if you have very little amount of noise. So going from one equilibrium point of V to another might take you a long amount of time. And this translates to how fast the probability density converges to this Gibbs distribution. And in practice, for most kind of data distributions, the potential is not expected to be convex at all. So for example, the set of like cat images and dog images and any other images that you expect the potential to be an extremely non-convex potential. So you don't expect this method to work very well. So how do we get around this? And this is one of the ways in which modern diffusion models have made a significant progress. And this is and this is what denoising diffusion methods do. So they've flipped the order in which they try to construct the map. And so instead of going from noisy images to meaningful images, the method of denoising diffusion first starts with meaningful images. And what does it do? It just adds noise to it. So you just take a pixel and you just flip it to some random value. So what would this do? This just takes your meaningful images and converts it into garbage, essentially. It's just white noise. And the idea of denoising diffusion is to now, given that we know how we can go in the wrong direction from meaningful to noisy images, can we somehow learn this map backward? So this by intuition, this seems like this shouldn't be possible, right? How do we recover how do we take complete noise and get something sensible out of it, like a sensible, like a face or the set of digits, as the case may be. And turns out this is possible if you, due to certain structural mathematical properties of the associated evolution of the probability distribution. And the idea behind it is this. So firstly, you have a set of equations which describes the noising process. And in this case, again, you have the Langevin equation. And what you do is you initialize the probability, initialize this dynamical system using whatever data that you have. Okay, so it's important to understand the distinction between what we're doing here and what I presented previously. So previously, when we were using the Langevin equation, we started with noise, but here we are starting with data. Okay, so here the potential V plays a very different role from from the role that we played in the previous method that I showed, which turned out to not work very well. So here the role of the potential V is to take you to noise instead of taking you to data. So you're starting with data, you're moving along some potential, and you're just adding some noise to it. And the goal is that you will eventually reach this noise distribution. And then you try to do what is so-called this denoising procedure. And the denoising procedure is basically it's a family or a class of another dynamical system which has the same statistics as whatever happened in the forward direction. So if you write down the equations, you can show that the probability evolution of whatever is the reverse process has the same statistics as whatever happened in the forward process. The key here is, of course, this identifying this reverse process. So it turns out that one choice of the reverse process is to take your vector field, velocity field, to be defined in the following way. You just take, so you see what happened in the noising stage, which gives you a family of probabilities. So we refer to this as P. And then you compute the score. So this is known as the score, but here it's just the gradient of the logarithm of the probability densities. And you set that to be a vector field. So it turns out the grad log of your probability densities, whatever you observed in the forward process, that if you just compute that, that's going to achieve this transformation in the reverse direction. And this is not the unique reverse process which does this. In fact, there are many other reverse processes which can do this, but all of them are constructed through this gradient of the logarithm of the probability densities. Or to be less wordy again, it's just the score. So this is why this is sometimes known as score matching diffusion. So if you can learn this object, you can basically go from noise to something meaningful, or whatever your original set of images was. So the idea behind denoising diffusion is essentially this, that you want to learn the score function, which takes you back from noise to the original data. And now learning the score just amounts to solving this regression problem. So your problem of achieving the data distribution becomes extremely simple. First, you run the noising process, you collect all the particle trajectories, and then you try to minimize the so-called score matching loss. And the nice thing about the score matching loss is it's just a regression problem. It's not a constrained optimization problem. which is what ends up happening in certain different methods like normalizing flows. You end up solving like a constrained optimization problem. So this is one of the reasons why it works so effectively, right? So because you're just solving a regression problem, and the convergence properties of this method partly depends only on the properties of the forward process, which is now governed by the properties of your noise distribution. So remember, I told you in the classical method, when you're trying to converge to your data distribution, it can be really slow if your potential is non-convex. Whereas here in the forward process, we are always trying to converge to the noise distribution. So the potential can be always chosen to be convex. So this means that your speed of convergence to your data distribution is it is just controlled by the noise distribution, is just controlled by the convexity properties of the noise distribution. So hence it can be pretty fast. And from a technical point of view, you can ask a lot of other questions. For example, does this reverse process have solutions? And so all of this depends on estimates of the gradient of the logarithm. And this will be relevant, especially for control problems, because we care about theoretical properties of the reverse process. So we'll come back to this. So now, how do we use this idea for doing control? To bring you back to my original motivation, it's to do control. So the traditional way to do control using this method of manipulating probability densities, a natural way would be, again, just to lift it in terms of probability density and to say that I want to go from some initial probability density to some final probability density, right? But now, inspired by machine learning and maybe the twisting arm of funding agencies, what if we flip this idea? So instead of going from an initial configuration to a final configuration, why don't we start from the goal configuration of your system, just make it go everywhere in space, and then somehow try to learn this reverse map? So this could be a useful idea. Say you want to plan in a domain with obstacles, right? So instead of trying to find a path to go from initial point around the obstacles to the final points, let's start backward. Let's start from the final point. Just generate a bunch of trajectories. Just sends you everywhere. And can we learn this reverse map? And hence look at control problems as a denoising problem. Somehow we are trying to denoise the family of initial conditions to a goal configuration. So it turns out this can be done. And you have to look at a modified form of these diffusion processes. And that is the goal. So that is one of the things that we did in this work. So our theory covers two classes of systems. One is driftless control systems and linear systems. Now, you might ask, why do we care about this method for linear systems? We already know how to control linear systems using standard methods such as linear quadratic control, which can be essentially solved as a finite dimensional problem. But there are different types of probability control problems which cannot be solved using standard techniques. For example, if you want to control the linear system to not just a point but to a different probability distribution, which can happen, say, if your linear system models a swarm of agents, right? And then you want to distribute it in space. So classical methods do not immediately apply to this more general probability control problem. So how do we do this? So we mimic the same idea. Instead, the same idea of noising, but we do it such that it respects the structure of the control problem. So in denoising diffusion in machine learning, you can apply noise in any direction. there are no physical constraints. However, in a control system, the noise can, in order to do noising that respects the structure, we add noise only through the control channels. So that's why you have this more complicated system of equations where you have noise that multiplies with the control vector fields and an additional term which plays the role of the potential. So you can go down a potential only along the control directions. So in terms of, going back to the original example of a car, you apply noise only in the steering direction and only in the forward and backward motion. So if you randomly perturb these two quantities, you will eventually just end up somewhere in space. In yeah. So if it's a closed domain, you could be anywhere after a long enough time with uniform probability. So this is a good candidate for a noising procedure. By the way, if anyone has any questions, feel free to stop me and ask questions. Yeah. I'm happy to be interrupted. Yeah. So now, in order to understand, of course, we've done the noising. We also need to know how to do the denoising. So once again, we need to understand how the probability densities evolve under the action of the noising procedure. So this requires us to consider a slightly more general kind of PDE known as the non-holonomic Fokker-Planck equation. I mean, I shouldn't say known. I think I'm the only one who calls it, but I thought it needs a name. And considering the well-known Fokker-Planck equation, which is the second equation over here, I think control engineers need a non-holonomic analog, which is the first one. So where instead of your usual differential operators, where these the Laplacian and the divergence operators are replaced by more general operators, which correspond to the control vector fields. So these operators are saying nothing more than that you're allowed to differentiate only in the direction of the control system. And that's because noise is acting only in the control directions. So one of the issues with dealing with this non-holonomic Fokker-Planck equation is that like why this problem becomes especially challenging in the control case is that the operators associated with these PDEs are extremely degenerate, and I wouldn't go into the detail of what it means to be degenerate, but in the case where you can add noise in all directions, you recover the so-called the heat operator or the Laplacian, which has a much bigger body of research associated with it. Basically due to the fact that you can add noise in all directions. So you have all the derivatives in the operator. Whereas in the control case, these, because you have only limited directions, these are harder to analyze. And so there are conditions under which these operators become not too bad. And this is related to control theoretic properties of the system. This essentially amounts to the question of when does your noising operation along the direction actually lead you everywhere in space, right? And this is actually nothing but a controllability problem. And what is a controllability problem? A standard controllability problem given your control system is given any initial point and final point, can you design a trajectory going from this initial point to this final point? So turns out the question of controllability is the same as the ability of performing noising, and it's identical mathematically to the question of whether these differential operators that you have are non-degenerate or not. So so turns out you can characterize this non-degeneracy using these properties of these drift vector fields using the notion of a Lie bracket, which if you've taken a nonlinear control theory class, you will probably come across this object, which is saying nothing but so these Lie brackets are capturing this idea that can you generate a new direction using your existing control directions. So in the case of a car, it means that, for example, you want to parallelly park a car. You can't, you don't have an immediate control which will parallelly park your car. But turns out using a combination of steering and backward and forward motion, you can generate a new lateral direction, a third direction. So it turns out your car is controllable. And hence this means that you can add noise to both your steering and forward and backward motion direction. And eventually your car will be can reach anywhere in space. And this amounts to the non-degeneracy property of the differential operator as well. And in the PD community, this is sometimes known as the Hermata condition, which is actually nothing but a controllability condition for your original control system. So it turns out whatever the control, loosely speaking, whatever is the controllability condition for your system translates to this Hermata condition. And you can basically use this to show that your noising process will eventually converge to the noise distribution. And this is something that I had shown with my advisor during my PhD, that if you apply noise with a specific choice of a potential, your control system would converge to this target distribution, even though you're not able to add noise in all directions. And for example, you have this case of a system moving on a sphere, and you want to converge to high densities in the north, close to the North Pole and the South Pole, and low densities everywhere in between. So turns out you can do it using this Fokker-Planck equation. So what this essentially means is that the noising procedure in the case of a control system is well posed as long as your system is controllable. And this makes sense because if your system is controllable, as you add noise, your system will spread randomly anywhere in space. And this means now you can define a well-posed reverse process. So now you can do a denoising. So basically you can denoise your control system as well using this score function. Except in the case of your control system, you end up with a generalized notion of a score, where you compute the derivatives only along the control directions. Once again, it makes sense because you can apply control only along the control directions. And turns out that this score function gives you a control law which takes you from any configuration in space and does exactly what the noising process did, except in reverse. And this holds true because you can write down the probability density evolution in terms of this continuity equation. So it solves exactly the PDF that you achieved in the forward direction, except with the time flipped. So from a control point of view, you can ask whether you can actually construct solutions of the ODE this way. So one of the theoretical goals of our work was showing that this ODE in reverse is well posed, so that we can eventually talk about questions such as stability, which is important in control theory. We want to answer standard questions such as robustness, stability, as the case may be. So why this question of existence of the control and the solutions of the ODE in the reverse direction is non-trivial is because these controls are usually not Lipschitz. They can be extremely irregular. They can because you're taking the gradient of the logarithm of a quantity, it can be unbounded in space. So it's not really trivial that you have a well-posed reverse process. But turns out you can prove this, and Hence, your reverse process is well posed. And now you can basically use the same algorithm which is used in machine learning to do denoising. To do control. So you first add noise in the forward direction, you collect all the particle trajectories, and then you solve this generalized form of score loss, which again, it's just a regression problem. You're not solving a constrained optimization problem with constraints coming from the dynamical system, which is one of the potentially nice things about this method, that it's just a regression problem, even if your system is nonlinear. And we have several examples. For example, path planning. If you want to converge to a goal point, you can frame this as if you are in a system, you are in a space with obstacles, and you just start with the initial configuration and you spread it apart in space. And then using this procedure, you can pose your planning problem as a denoising problem. So here you can see that this denoising is achieved, right? You can find trajectories. But I just want to clarify that here I'm only showing the successful cases. It's not always as nice and pretty, especially if your obstacles are nice. The neural network, oh yeah, I was supposed to, this is supposed to be a machine learning inspired approach. I didn't even mention neural networks. But usually you use a neural network to learn this score function. And it can take a lot of tweaking to achieve this. So sometimes you have failure cases as well. But the essential point that I want to make is not that this will solve all your problems, but that I think this is giving you an interesting alternative to the existing methods and control, because this idea of time reversal is, I think, genuinely extremely new in the control theory community. So the fact that it gives you a universal way to do stabilization as well as planning is, I think, extremely interesting. Um, and I don't think there are very few truly universal ways. One of them being by solving a Hamilton-Jacobi equation. There are very few universal ways that apply to all classes of systems. So time reversals seems to be one such approach. And as I said, and this can apply to nonlinear, the unicycle model as well, where you start from where. So the first example that I showed you, I didn't include any control system dynamics. It was just there was noise acting in all directions. In this case, this is like a robot which does only steering and turning, right? So you add noise in all directions, and then similarly, it can denoise the system. That is, So this is again one of the advantages, that usually control theorists are bad at solving the planning problem. Roboticists have their own way of doing it, and it's generally been the case that we are good at solving local stabilization problems. But this gives you a way to potentially solve the planning and the stabilization problem simultaneously. But of course, this is not completely without its issues. For example, you can kind of see that qualitatively it's converging to the equilibrium, but it doesn't. But there are still points away from the obstacles. And you can do this for larger obstacles as well. Here you can see that though in theory, the probability density should end up converging to the equilibrium points, there are still some points which are kind of stuck around the obstacles. So maybe if we had a better way to learn the neural network, it'll we can ensure all the points. But this kind of shows that even though in theory we know we can guarantee that it'll all converge to the equilibrium, there are still some numerical issues in the way this is solved. So there's a lot of scope of improving this method. And this method can also be applied for higher dimensional systems. Of course, I'm not saying that we can avoid the curse of dimensionality, because you would just need a larger and larger neural network. And Yeah, but we could at least approach things of moderate dimension. For example, this system. By the way, both of these systems, this 5-dimensional system and the unicycle model, it's also challenging to use methods such as like just constructing Lyapunov functions to stabilize these systems, because of inherent problems in the geometry of the system, right? And so these are also challenging from a classical control point of view. But here you can see that uh, we can stabilize it. So we use a cost known as the KL divergence cost. And one of the things this plot is showing is that you need larger and larger number of samples in order to get a lower, to design the control, right? So if you just use 300 samples, you can the controller that you will get would be terrible. And so there's some relation between how good the computed control is and the number of samples that you use. So implicitly, this is where the curse of dimensionality would show up. And then you can also use this to solve problems, non-conventional problems for linear systems. For example, if you want to control your linear system not to a single configuration, but you want to split it into multiple different configurations. So you want to introduce some kind of bistability in the system. So this can also be posed in terms of probability densities, probability distributions. That is, you're trying to control the system to two Dirac masses sitting at this configuration -5 and 5 and 5 -5. This again cannot be posed as a standard control problem. So this denoising approach gives you a nice alternative to do this as well. And so, especially in the linear case of the linear system, a lot of simplifications arise. You can do this denoising just using the controllability Gramian of the system, uh, which is a quantity that you can compute for at least moderately high dimensions, because it's just like computing an integral for using the system matrices A and B. Yeah, so that's the end of my talk. This was joint work done with Darshan Gadginmat and Fabio Pasqualetti at UC Riverside. And we presented one paper at IEEE CDC, and then we have the journal version of the paper, which is now posted, which is a preprint posted on arXiv. There are a lot of open questions. One is about the speed of convergence to the noise distribution, which affects the performance of the controller. So in machine learning, the speed of convergence just depends on the convexity of the potential, whereas in control, this is a much harder question to answer because of other aspects of the problem coming in. Another issue is from the issue of implementation. The controls kind of blow up in value, which is something you do not want, especially if this control is you're sitting in a car which is doing denoising control. You don't want it to suddenly blow off a tire. And then there are other questions that that control theorists care about. You can ask, what are the stability properties of the system? Can we give classical guarantees in this framework? But yeah, that's about it, and I can take any questions. Thank you.
Thanks a lot for this talk, Karthik. Does anyone have any questions? I'll start with a couple of questions then. Is there a parallel here with dynamic programming? Because you mentioned the Hamilton-Jacobi-Bellman equation. Normally, you start at the terminal state and solve the problem backwards. Could what you're doing, could that be interpreted as approximately solving the Hamilton-Jacobi-Bellman equation for random initial conditions?
This is an interesting question, and yeah, I've definitely thought about the parallels, and wondered if it's true. And I think the answer is no if your time horizon is large, because the trajectories that you're constructing in this forward direction are just extremely you're just adding random noise. So there's no reason for the reverse process, the trajectories of the reverse process um, to be optimal trajectories. And you can see this even in the case of like without the control. Like if um, if you were just solving the original machine learning noising and denoising problem, and the reverse process was somehow optimal, you would expect all the trajectories to be straight lines. Because when you have control in all directions, if you're somehow solving the minimum energy problem, the optimal solutions should be straight lines. So it turns out that's not the case. But what might be possible is that if your time horizon is really small, I think so. The noising procedure can be infinitesimally acts. It's so there's this result called the Vardhan I think it's like some asymptotic result that for small time horizon, the noising problem effectively approximates the optimal path between 2 points. So it might be that for really small time, the solution of the noising and the denoising procedure actually ends up converging in some asymptotic sense to the Hamilton-Jacobi equation to some for some cost. So, but yeah, it's similar in flavor, and maybe in some instances, it is doing solving the AJB equation, but in a completely different way.
So are you saying in the forward process, the trajectories move randomly, and then in the
Yeah.
backward process, when you denoise, you're trying to retrace those random motions back to the original distribution, and that might be non-optimal.
No, so that's the thing, and that's one of the things about denoising is that when you're doing denoising, you're not actually trying to learn the noisy trajectories in reverse. You're only trying to mimic the statistics in the reverse direction. So though the particles as a whole might look like they're achieving the same behavior, in fact, the microscopic level, the trajectories are much smoother because it's solving a ODE. It cannot behave in a very erratic way.
Mm.
So, so the reason I'm saying it's not solving the HAB is not because of the fact that it's doing this reverse. It's just that it, the solutions of the ODE, though they are not erratic, they just end up being different trajectories. And like you can see this for the heat equation and the usual noising as well. And in fact, someone has even written that because this was postulated in when denoising diffusion came out, that for certain instances, is denoising diffusion just constructing the optimal transport between initial to final distribution? And someone wrote a proof that this is not the case. And so, by analogy, in the control case as well, I would not expect it to be giving us the optimal control map.
Okay.
Mhm.
Do we
But I
have
think
any
it's a
other
very deep
questions?
technical question that yeah.
Any other questions? Could ask another question then.
Yeah, sure.
In the machine learning problem, you said it's only solvable when you select this V that gives you your target distribution to be like
Right.
strongly convex.
Right.
In the control problem, since you're putting the noise through the dynamics,
Right.
you don't have complete control of the final distribution, and is it true that it could be non-convex based on the dynamics?
So when you do this noising procedure, you can take your potential to be whatever you want it to be. So you can choose it to be convex or non-convex. But so though you have this choice and it'll converge to, so in the noising procedure, you're trying to converge to some uniform distribution. So though you have this freedom of choice, you cannot say that because it's convex, it'll converge pretty fast. In the case of when you have control, and this is because the control vector fields induce, like, they add kind of another layer of non-convexity to the problem, which makes it hard uh, j- to show the speed of convergence. Did that answer your question? Or
Yeah. So you're saying depending on the dynamics, for any choice of V, you could still have issues with convergence.
yeah, you could have extremely slow convergence even if V is convex
Yeah.
if you have a control problem. That's the yeah.
Okay. Final question from me then is if you're solving these planning problems and you want to start from a specific initial condition, do you
Mhm.
have to wait for the forward process to find this initial condition before applying these denoising methods?
Okay. So this method is like terrible if you want to solve this problem just for one initial condition. Because then I mean, essentially, it's like solving an open loop control problem, right? You want to go from point one to point B. So what this method is good at is um, giving you a feedback control that is from all initial conditions. Because if you just want to solve from one initial condition, as you said, you will basically just generate one trajectory till it ends up at that point. And this method just breaks down if you just want to solve it for one initial condition, because you won't have a probability density. You would just have like a single particle, and you can't denoise a single particle trajectory. So, so this method is only meant when you have a family of initial conditions, because only then you can kind of, when you do this denoising, it'll kind of spread everywhere. So you kind of visited every space. Whereas, as you said, if you just want to solve it for a single initial condition, you could just, you could keep, basically, it's like, yeah, you could take forever to reach that initial condition. And it's not a good method for that. It's not
Even
an
if you have
alternative to
a
open loop.
family of initial conditions, depending on
Sorry?
the dynamics, even in the case with a family of initial conditions somewhere, depending on the dynamics, could you still be waiting a very long time, maybe an arbitrarily long time until the forward process sufficiently covers your family of initial conditions?
Yeah, and that's where the it's important to understand, I think, the speed of convergence, because the speed of convergence is essentially telling you how fast you spread out in space. And whereas in the machine learning case, you can say that if V is convex, you will spread everywhere in space pretty fast. You cannot say this in the case of control. And it basically is related to your previous question, is that, yeah, because you might have a convex V and you could take forever to spread uniformly in space, right? And this is basically like, you're trying to get to the parallel parking configuration, and by adding noise, how can you get to all the parallel parking configurations, right? Like, it might require too many oscillations for you to get there. So this is intricately related to basically these Lie brackets, and how many times you need to switch between these vector fields so that you generate new directions. So that kind of governs how fast the noise acts in the directions that you can't control in. So yeah, it could take long, and these are kind of open questions around this method.
Okay.
Mhm.
Um, well, does anyone have any other questions? You can also drop them in the chat. It's the last chance to ask since the 5 p.m. UK time now. So
Okay, everyone's, yeah, ready to head home.
I suppose if anyone has any other further questions, they can always email Karthik. I
Yeah.
think, was your email on your slides? I think it was.
I'm not sure my email was, but you can easily find it from my website.
Yeah.
Sure. Yeah, I'd be happy to take questions. Yeah. Thank you, Morgan, and everyone else for having me. Yeah. Okay.
Yeah. Thanks for coming. Yeah. We'll put an end to the seminar and
Okay.
yeah.
Cool. All right. All of you have a good evening. See you. Bye.
Bye.